Section: Abstract. In this section, we present a straightforward approach to evaluate the reliability, stability, and interpretability of any black box large language model, LLM, in real time, based on the local deviation from harmonicity, denoted as gamma. As far as we know, this is the first method that is completely model agnostic and unsupervised for assessing the reliability of any given response from an LLM, by examining if the model adheres to a strict mathematical standard. We carried out human annotation experiments to demonstrate the positive connection of gamma with incorrect or misleading responses. We also show that by following the gradient of gamma using stochastic gradient ascent, we can effectively uncover adversarial inputs. By calculating gamma for numerous queries in popular LLMs like GPT-4, ChatGPT, CLAUDE 2.1, Mixtral 8x7b, Smaug 72b, Llama 2-7b, and MPT-7b, we can estimate the likelihood of incorrect or hallucinatory responses automatically and rank the reliability of these models across different domains: Web QA, Truthful QA, and Programming QA. Our findings reveal that a gamma value close to 0 indicates trustworthiness, and the models with low gamma values include GPT-4, ChatGPT, and Smaug 72b. Motivation and introduction. Large language models, LLMs, are often very confident in their responses, which can be challenging for users seeking factual information. With hallucinations being a common issue in LLMs, there is currently no reliable way to assess the trustworthiness of a response without extensive verification. What users lack in their interactions with LLMs is a trustworthiness score that can indicate whether a response is reliable. The ultimate aim is to have LLMs that consistently receive high trustworthiness scores, reducing the need for users to verify responses independently. We propose that a trustworthiness score can be achieved through harmonic robustness, a method introduced in a previous study to evaluate the robustness of predictive machine learning models. In that study, it was shown that computing the anharmonicity, gamma, in any black box model was linked to the model's robustness, stability, and interpretability in feature space. This current study extends the application of harmonic robustness to LLMs, which, despite being next token prediction engines, have unique characteristics that warrant a separate analysis. The core concept of harmonic robustness is to measure how closely a machine learning function f aligns with being harmonic, meaning that the function's value at any point is the average of the function over a surrounding area. This property signifies stability and interpretability in the function. By applying this concept to classical ML models, one can identify points where the model's output should not be trusted. However, applying this to LLMs comes with challenges, particularly due to the stochastic nature of LLM outputs and the need to interpret string inputs. To address these challenges, we introduce the notion of adding random non-printing characters to input strings to assess the stability of LLM outputs. A significant variation in output indicates instability, while a consistent output, with gamma equals O, suggests stability and alignment with the model's training data. We believe that measuring sensitivity to the harmonic condition, as represented by gamma, can help identify unreliable responses in LLMs. In the subsequent sections, we will delve into the technical details of adapting harmonic robustness to LLMs and demonstrate how gamma correlates with trustworthiness in human annotation experiments across various popular LLMs and domains. Section Summary. Abstract. In this section, we introduce a novel method to assess the robustness of black box large language models, LLMs, in real time by measuring their deviation from harmonicity, denoted as gamma. This model-agnostic approach correlates gamma with the likelihood of incorrect or hallucinatory responses, allowing for the quantitative ranking of LLM reliability across various domains. The method, applied to popular LLMs like GPT-4 and ChatGPT, reveals that low gamma models such as GPT-4 and ChatGPT are more trustworthy according to human ratings. Section: Related work. In this section, we delve into the evaluation of language model, LM, robustness, which is crucial for assessing how well models perform under different input conditions, such as noise and adversarial prompts. The Flask method has been key in evaluating LLMs by checking the consistency of their scores across various input styles, emphasizing the importance of aligning skill sets for detailed model evaluation. However, vulnerabilities found in these evaluations have raised concerns about the model's susceptibility to manipulative inputs, casting doubt on the reliability of such assessments. Instruction-tuned LLMs have struggled to maintain performance when given rephrased instructions, leading to the development of methods to enhance their ability to handle new tasks without prior training. The Prompt Bench framework introduces a structured way to test LLMs' resilience to adversarial prompts, highlighting the need to understand how models react to different input changes. Insights from evaluations by Eleuther AI have deepened our understanding of LLM performance and robustness, emphasizing the importance of models that can interpret a wide range of inputs reliably. Recent research has explored adding noise to input prompts to evaluate LLM robustness. A unified framework has been proposed to systematically assess LLM performance in noisy real-world scenarios. Additionally, advancements in differentially private prompt learning have focused on creating noisy sets of private prompts, showcasing new techniques for preserving privacy while learning from prompts. The selection of prompts plays a critical role in ensuring accurate model responses, with studies showing how noisy annotations can affect model performance. Addressing vulnerabilities in LLMs when faced with noisy inputs, especially in high-stakes situations, is crucial for ensuring stable predictions. Our research emphasizes the importance of maintaining consistent LLM predictions despite minor input changes, aiming to develop robust LLMs. We propose a self-denoising approach to clean corrupted inputs, which differs from previous methods requiring a separate model for robustness training. Studies on measuring an LLM's confidence have gained traction, with methods leveraging prompting, sampling, and aggregation to assess confidence levels. Techniques like chain of thought use LLMs to reflect on result consistency, providing new ways to measure confidence. Research on LLM robustness to input changes, closely related to our approach, has been present in natural language processing literature for years, suggesting that some sensitivity to perturbations will always exist. Section Summary. In this section, we delve into the evaluation of language models, LLMs, and their robustness to input variations, particularly focusing on noise and adversarial prompts. The Flask method has been pivotal in assessing LLMs based on the consistency of their scores across different input styles, emphasizing the importance of alignment skill sets for precise model evaluation. Our approach, Harmonic Robustness for LLMs, involves perturbing input strings with random ASCII control characters to measure the stability of LLM predictions, highlighting the need for models that can maintain consistent outputs despite minor input changes. Section: Performance on Standard Question Sets. In this section, we will assess how well our gamma metric aligns with trustworthiness by evaluating outputs from 7 different language models, LLMs: GPT-4, ChatGPT, Claude 2.1, Mixtral 8x7b, Smaug 72b, Llama 2-7b, and MPT-7b. We will test these models on 3 question-answer corpora: Web QA, Truthful QA, and Programming QA. Our aim is not to cover all LLMs or question types comprehensively but to showcase the utility of gamma. We randomly select 100 questions from each model for each corpus and have unbiased annotators rate the relevance and correctness of the model's answers on a 5-point scale. For coding questions, we adjust our evaluation criteria as coding requires precise answers. We observe consistent agreement among annotators, with Fleisch kappa around 0.6 for all 3 domains. The larger models generally receive high ratings, greater than 4, indicating satisfactory performance, while the smaller models struggle with quality issues, especially in Truthful QA and Programming QA. Interestingly, we find that responses with low gamma values, below 0.05, tend to be more trustworthy, scoring 4 or higher in our evaluations. This suggests that LLMs with harmonic, gamma close to 0, responses are reliable. We notice a trend where higher gamma values often lead to lower quality, although this varies across models and domains. Larger models like GPT-4 and ChatGPT exhibit lower gamma values compared to smaller models like Llama 2-7b and MPT-7b, indicating higher trustworthiness. By comparing quality and certified trustworthiness rankings, we identify the top-performing models across the three domains. Additionally, we analyze the distribution of gamma values for each model across a larger sample of questions from the three corpora, revealing insights into model trustworthiness. Overall, our findings highlight the importance of considering gamma values in assessing LLM performance and trustworthiness. The gamma distributions demonstrate the advancements in LLM technology, with newer models showing improved trustworthiness compared to older ones. This unsupervised metric provides a valuable tool for evaluating LLM reliability in various contexts. Section Summary. In this section, we evaluate the performance of various large language models, LLMs, including GPT-4, ChatGPT, Claude 2.1, Mixtral 8x7b, and Smaug 72b, as well as smaller models like Llama 2-7b and MPT-7b, across different question-answer corpora. Our analysis shows that LLMs with lower gamma scores, indicating harmonic behavior, tend to provide more trustworthy responses, while higher gamma scores may lead to more unstable rephrasing of answers. Larger models like GPT-4 and ChatGPT exhibit lower gamma values and higher trustworthiness compared to smaller models, highlighting the progress in LLM technology over time. Section: Adversarial Example Discovery. In this section, we explore the discovery of adversarial examples. We found that the gamma metric can help us efficiently uncover adversarial prompts. By following the gradient of gamma, we can identify adversarial examples that are more likely to appear along this gradient. For instance, when we began with a prompt related to particle physics, seeking misinformation about the 9 quarks in the standard model, which actually has 6 quarks, we manipulated gamma by adding random UTF-8 characters instead of ASCII control characters. This led to the generation of false content after just one iteration and complete fabrication after 2 iterations. Similarly, when we made a light-hearted request for a cookie recipe including xenon to GPT-4, the initial response was a polite refusal due to safety concerns, revealing some gaps in the model's knowledge about noble elements. By iteratively adding random UTF-8 characters in the direction of increasing gamma, we eventually persuaded GPT-4 to provide a recipe with xenon, albeit mixed with nonsensical information.